Okay, thanks very much for the invitation. Thanks for coming. So I'll be talking today about the relation between robustness of deep neural networks and the geometry of the classification objects. So as Anders just mentioned, deep learning has been phenomenal in improving many applications ranging from classification, image captioning, speech recognition, playing complex games like the game of Go and StarCraft and so on. And particularly in the task of image classification, there's been huge improvements in the recent years where we've went from more than for example, 25% error rate on a very complex classification tasks, that of ImageNet that comprises thousands of labels and millions of images, to less than 5% in 2015, which is quite some time ago, which is on par with what actually the human is actually able to do on such a complicated task. Now, despite this huge improvements in the recent years, there's still many challenges that we need to tackle before basically deploying these in real-world environments. And today I'll be talking specifically about the robustness of deep neural networks. In particular, we want deep neural networks to work, to be able to classify images even if they're not so clean. So what do I mean by this? Well, I mean that let's say that you have an image here of a lampshade, okay? And you perturb this image just a little bit, for example, here through a geometric transformation, and you classify basically this perturbed image. You want the perturbed image to have the same label as the original image, okay? So that's what I mean by robustness here. In particular here, the robustness to geometric transformations. Now, depending on the application, there might be many different perturbation regimes we're interested in. For example, we might be interested in a robustness to adversarial perturbations, where you have a malicious agent that basically tries to add the minimal amount of noise to your image in such a way to cause data misclassification. You might also be interested in other types of noise, such as random noise, for example. Or in computer vision applications, you might be interested in structured nuisances, such as geometric transformations, occlusions, illumination changes, and so on and so forth. So that really depends on your application of interest. So I'll be talking specifically today about adversarial perturbations. Okay, but before delving into the main subject of the talk, I'd like to highlight why I'm actually interested in robustness of classifiers to perturbations, and this is something that I've been working on for a few years. I think the first motivation, which is probably a bit obvious, is that robustness and safety are extremely connected, right? So if you have, for example, a self-driving car which uses a classifier, right, and takes important decisions, such as, for example, overtaking and stopping at the stop sign and so on, you really want these actions to be performed in a robust way. You don't want a very small perturbation to the data feed to make it go completely wrong, right? So that's the first aspect of it. But more importantly, I think, or more fundamentally, I should say, at least what I'll be trying to convey today is that there is a fundamental link also between robustness and geometry of deep neural networks. So in particular, our understanding, if we try to understand better the robustness aspect of deep neural networks, we are going to understand better the geometry of deep neural networks and vice versa. So in particular, we'll be trying to understand what is the relation between the robustness of deep neural networks and the decision boundaries and the curvature of the decision boundaries, for example, of deep neural networks, and show that this is not only for analysis, but we can leverage this in order to improve those robustness properties. Those geometric properties can be used to improve robustness to adversarial perturbations. Okay, so I'd like to convey today three messages. The first message that I'd like to convey is that fooling classifiers is an extremely easy task. So I've been working on this for a few years, and really, I should say that anything that I've tried basically worked in order to fool the classifiers. So anything that you actually come up with, it is very likely to work in order to fool the classifier. And we'll see this in more details. On the other hand, improving the robustness of classifiers is an extremely difficult task. So how many times we actually thought that we were improving the robustness of classifiers, but then it was actually not doing this, but it was more like obfuscating the model or something like that. We'll go through this in more details. And then the main bulk of the talk is going to be more about like taking one specific defense, which has been very successful in the last few years, which is adversarial training, one of the most basic defenses, and trying to basically explain it and understand it from a more geometric perspective. Okay. Okay. Okay, so first things first, I guess we all know by now that state-of-the-art deep neural networks have been shown to be extremely unstable to adversarial perturbations. So what does this mean? Well, it basically means that this is an image of a school bus, right? And correctly classified by a deep neural network, state-of-the-art deep neural network as a school bus. And this is an image that is classified by the deep neural network as an ostrich. Right, so you might not see any difference between these two images here, except that there has been added, like we have added a very small perturbation on the left-hand side image in such a way to basically cause data misclassification. Okay, so this perturbation here has been sought in order to basically cause data misclassification. So I'd like to emphasize that this is not random noise. So this is something that really like we optimized for, like we got from an optimization process, okay? And we have added on the right-hand side, on the left-hand side image that resulted to the right-hand side image here, and that is completely misclassified, okay? Okay. So from a more like pictorial perspective, what is actually an adversarial perturbation? So assume that you have a binary classification task, a two-dimensional binary classification task, where here you have like images of class 1, say cats or something, and here you have images of class 2, say dogs or something. And we have the data point here, which is like a cat, for example. And the robustness to adversarial perturbation is nothing but this vector here that you add to X in such a way to go to the other side of the decision boundary. So the frontier here between these two classes is what we call the decision boundary. Okay, so like more formally, what is actually the robustness to adversarial perturbation? It's actually you're trying to solve this optimization problem where you're trying to find the minimal perturbation that you need to add on the data point X in such a way to basically go to the other side of the decision boundary. Okay, so if we take for example as the norm the L2 norm in this case. Okay, so we're trying to minimize the L2 norm of the perturbation in such a way that when you add X to R to this perturbation, you basically the classifier is completely misclassifies X plus R. Okay. Yeah. Okay. Okay. So since the discovery that deep neural networks are extremely vulnerable to adversarial perturbations, there's been a huge amount of work to try to simplify this perturbation regime and go as simple as possible. So, for example, there's been works on universal perturbations where you basically try to find a single perturbation that basically fools most images. Okay, so note that in the previous slide, the perturbation that we compute is actually very data point specific, so it depends on X. But now we're trying to find a perturbation that basically works for everything, or for most of the images. Okay, so we're trying to find this single pattern here in the center of the image in such a way that if I add it to the image of a joystick or a flagpole or a balloon and so on, you basically get images that are extremely similar in terms of visual appearance to the images here on the left, yet result in a completely different label. And indeed, we've shown that indeed it is possible to find this single pattern that you need to add in order to cause data misclassification on most of the data on images, basically. Now you can even go further and say that okay, I don't want to find this perturbation in this high dimensional space, but I actually want to find a perturbation that is meaningful in a low dimensional manifold, such as, for example, you'd like to find an affine transformation, or you'd like to find a projective transformation or something like that basically fooled your data points. And indeed, it was shown indeed that it is indeed possible to slightly transform the image in order to fool your classifier. Okay, so in this case, the transformation is actually has a very low degrees of freedom, unlike adversarial perturbation, where you have like a d degrees of freedom, the number of pixels, right? So indeed, even in this restricted setting, it is possible to find adversarial perturbations. So so this has the fact that there's been a huge amount of attacks that have been developed in the last few years, and people have created benchmarks to basically evaluate your model against all these different benchmarks, and this has led to good efforts that basically where you submit your model and you get basically this evaluation of your model against all these benchmarks. Now, this is the side of the attack. Okay. Now, on the other side, basically the defense side, things are completely different. So finding adversarial perturbations is extremely easy, but finding designing defense mechanisms are actually extremely hard. So there's probably been thousands of papers, I'd say, or yeah, hundreds of thousands of papers on designing defense mechanisms. But unfortunately, many of them have been shown to actually not be proper defenses. In that they basically obfuscate the model rather than creating basically robust models. This has been pointed out by these two ICML papers, ICML 2018, where they basically take a series of different defenses and basically break all of these one by one, except adversarial training. So what do I mean by actually obfuscating the model? Is that you're basically trying to create a perception that your model is actually robust, but if you actually make your attack a bit stronger, if you make your attack a bit, let's say you run more iterations of gradient descent or something like that, you basically can still fool the model. Okay, so it is like these defenses were more like making the classifier robust against a specific attack, but not against all attacks. And this is really what we are targeting here. We're trying to make the network robust against all attacks. So since these two papers, there's been a huge amount of papers on trying to basically take previous defenses and breaking them. So there's been this back and forth between designing a defense and then breaking it, and then designing another defense and then breaking it, and so on. And that's basically the state of the community right now. Except that there is probably one defense or a few defenses, I should say, that have not been able to be broken by designing more complex attacks. And specifically, this attack is adversarial training. Okay, so this is basically the simplest attack, the simplest defense, sorry, you could think of. So adversarial training is this procedure where you, instead of training on the original samples, on the clean samples basically, you perturb your images and then you train based on these perturbed images, okay, in an online fashion. Okay, so let's say we have a data point X, which is clean. What I'm going to do is that I'm going to compute adversarial perturbations on this data point based on the model that I have currently, okay? This will give me R perturbation, okay? And then I'm going to basically do a training based on this X plus R instead of X, okay? And then I'm going to update the model based on this X plus R, and then I'm going to recompute adversarial perturbations based on this updated model, okay? So I'm emphasizing on the fact here that adversarial perturbations are computed in an online fashion. So at each iteration of your algorithm, you actually compute an adversarial perturbation, and then you add it to the training data, and then you update, and so on and so forth. Okay. So if you want to make adversarial training to work, you have to have two components. The first one is that adversarial perturbations have to be computed in an online fashion. Okay, like you cannot use like very old adversarial perturbations, not for the current model, for example. The second component is that you need actually to compute strong attacks. You cannot use like a very easy attack, like a one-step attack or something like that, in order to compute R. So you really need to spend a lot of effort to compute this R in order to find the adversarial perturbation. Okay. Let me know if it's not clear, this adversarial training procedure. Yeah. Okay, so now let's see what is the effect of adversarial training on our network. So if I take a standard benchmark such as that of CFAR10, for example, you get an adversarial so your adversarial accuracy is 0%, meaning that you can fool basically all data points if you train it in a normal way. Now, if you train it with adversarial training, you get basically a significant improvement in the robustness of classifiers to adversarial perturbation, meaning that you can only fool roughly 50% of your data points, but still the other 50% you can still fool them, which is, so 50% is not that great, but at least it's an improvement over the 0% that we're getting with normal training. Okay. Okay. So this has been like an important. So this has been an important like training mechanism to achieve robustness of classifiers to perturbations, but we still don't really understand what it's actually doing. Okay, so what I'd like to talk about in the next few slides is actually what is it doing from a geometric perspective in order to improve this robustness, and what can we understand from it, what can we take from it in order to improve the robustness without going through this very expensive procedure of adversarial training. Okay, so the first thing we can do is basically to plot decision boundaries, and I really like to do this because it tells you a lot. Like even if our data is like 3,000 dimensional, for example, in CFAR, even plotting 2-dimensional cross sections is actually very useful. So let's see what happens. So we consider a 2-dimensional cross section of like one direction is a random direction and the other direction is an adversarial direction. Okay, so if I plot the decision boundary for a normally trained network, this is basically what I get. So here in the center of this image here, I have the data point, okay, and here I have class 1, and here I have class 2, okay. So so basically the robustness to adversarial perturbation, as we've seen in the last few slides, is actually this distance here, right? Okay. And that's why, yeah, so that's why the distance here is much smaller than this, because like adversarial direction is the vertical direction, okay? Now, if we do adversarial training, this is what we get, okay? So you can see two differences between the left plot and the right plot. The first difference is that this distance has significantly increased, right? This distance here has significantly increased, which is something that we expect, right? We want the robustness to increase, so yeah, that increased. But the other thing also is that you can see that the decision boundary has become significantly flatter, right? Like the curvature, in other words, has significantly decreased. So this is something that is quite interesting, and we'll have a look at it more. But the problem is that quantifying decision boundaries is actually a difficult task. In other words, the decision boundary is a complicated mathematical object that is very hard to work with. Like it's hard to compute the curvature of a decision boundary, for example, because it's hard to quantify it basically. So instead of working with a decision boundary, we're going to work with a proxy of it, which is the loss function. Okay, so so the loss function with respect to the inputs. So I'm emphasizing on the fact that we're going to study the loss function with respect to the inputs and not with respect to the weights, which is usually what's done. So the loss function with respect to the inputs here is the cross entropy loss between basically the output of the network, okay, which I call here f theta of x, and my label y. Okay. Now I can plot also this loss function with respect to the same plane that I was plotting before. So this direction is an adversarial direction. This direction is a random direction. So that's basically the negative of the loss function. Okay, you get something like this. Now after adversarial training, you get something like this. Okay, so you get something again that is significantly smoother, the curvature of the loss function has basically significantly decreased after adversarial training. We can also follow this this evolution like through adversarial fine tuning. Like we train a network normally, and then we fine tune based on adversarial training. And you can see here that indeed the effect of adversarial fine tuning is to make the loss function significantly smoother here. So that's before like the first frame was before adversarial training, and it basically evolves to like this is basically a few iterations of adversarial training. Okay, so that's from the qualitative side of things. Now we can also try to understand, like we can try to quantify basically whether this curvature is indeed decreasing or not, because at the end of the day we're just plotting things in 2 dimensions, so you don't know what's happening really. So we can quantify this by basically computing the Hessian, which is the second, I mean you don't know what the Hessian is, yeah, so we compute the Hessian, and then we compute the eigenvalues of the Hessian, okay? which basically tell you information about the curvature at the data point x. And this is basically the curvature. So we are working on CFAR. CFAR is a 3,000 dimensional problem, so you get 3,000 basically eigenvalues. So this is the curvature basically of the Hessians, like the eigenvalues of the Hessians before adversarial training. So with an original training, and this is after adversarial training. So you can see that basically the curvature are extremely smaller after adversarial training than before. Okay, and also that the curvatures are actually quite sparse, which is interesting by itself. So yes, indeed, if we quantify this, we also get this phenomenon of like that the loss function becomes more linear after adversarial training. Now we can also like try to quantify the relation between robustness and curvature more mathematically. I won't go into details, but we can basically do a quadratic approximation of the loss function, and then this allows us to derive upper and lower bounds on the minimal perturbation that is required to fool the classifier. I just will highlight this result in a very simple, like one-dimensional example. So just to mention why is curvature related to robustness. So let's say that we have our data point x0 here, and the robustness to adversarial perturbation is basically the distance that you need to go from x0, the data point. So the distance in order to basically go beyond this threshold. So let's say this threshold is the threshold after which you get misclassified. Okay, so if this is my loss function, then the robustness to adversarial perturbation is this distance from x0 to xadv that you need to go in order to basically go beyond or above this threshold here, because that starting from here things become misclassified. Okay, so if my loss function here is linear, then obviously this distance is large, but as the curvature gets higher and higher, obviously what you'll get is that this distance between x0 and xadv will actually get smaller and smaller. Hence the high relation between robustness and curvature. So this this very simple idea extended to high dimensions allows you to derive basically upper and lower bounds on the robustness of classifiers with respect to the curvature. Okay, so how much time do I have?
We've got another
15 minutes. Okay.
So 20 minutes.
Okay.
Yep.
Cool. Okay, so now we've seen that basically adversarial training has this effect on the curvature of the classifiers of the loss function, but we're still not sure basically that this is the main effect that improves the robustness, right? Because we know that adversarial training leads to smooth loss function or like low curved loss functions, but then it might be a more complex phenomenon that basically leads to this robustness, right? So in order to verify this, the intrinsic link between robustness and curvature, we will basically regularize for the curvature explicitly and see whether we gain the benefits of adversarial training by doing so. Okay. In other words, we want to understand if the curvature is the main effect that of adversarial training that leads to improved robustness. Okay. So in order to do this, we basically regularize the norm of the Hessian with respect to the inputs. But obviously the Hessian is a complicated, is a high dimensional matrix that is hard to work with. So instead of like regularizing the Hessian immediately, what we're using is this estimator here that only needs Hessian vector products. In practice, what we actually did in order to regularize for this Hessian is that we computed this Hessian vector product using finite difference. Okay. And note that here we need to sample, like if we want to compute this, we need to sample in this normal distribution here. But what we did in practice is basically we leveraged the sparsity of the curvature here in order to sample only in the curvature in the directions that lead to high curvature, like and not sampling across all directions here. Okay. So if we basically do this selective sampling and using finite difference, we can have a fast estimator of the Hessian, and then we regularize basically we regularize this quantity, which basically captures the second order properties of the loss function. Okay, and we call this the curvature regularization because like it's like cure for curvature regularization. Okay. Okay, so then we can basically try to see the effects of using this procedure cure in order to improve the robustness. So recall that our normal network was achieving roughly 95% accuracy on the clean samples, but 0% accuracy on the adversarial samples. And recall that adversarial training was having like a slightly smaller accuracy on the clean samples, but like it significantly improved the robustness to adversarial perturbations, as seen on the right-hand side here. Now, if you use this cure, which is just about like regularizing the curvature, you do get indeed this improvement in the adversarial accuracy, even though we did not do any adversarial training. The only thing we did is regularize the curvature of the loss function, and we got this robustness to adversarial perturbations for free. Okay, so this is really telling us that this relation between robustness and curvature is the driving effect, or one of the driving effects, or like that the curvature of the loss function is one of the driving effects that leads to an improved robustness. Okay. So yeah, there is this two-way link between like adversarial training and reduction of curvature. And in a recent work, we've actually been able to go well beyond this this adversarial training result on CIFAR and ImageNet using this very simple idea of reduction of curvature. So it's not something only that is used for analysis, but we can use it also to improve like to go beyond adversarial training and to get much cheaper attacks. So yeah, I should mention here that one of the nice effects of making your loss function more linear is that you really don't need to have very complex attacks in order to fool your classifier. But if you think of the loss function to be roughly linear, then you really need to do just a few steps of gradient descent in order to get the best attack possible, right? You don't need to have something that is very, very complicated, and that makes your life much easier in order to attack your model, or in order to make sure that your model is like you're evaluating your model against the strongest attack, basically. Okay, so now I'd like to talk a bit about like why is this percentage is so low, right? This is like 50%, which is still significantly smaller than what we think we can get as a robustness, right? So I think one of the keys in order to understand this is that there is fundamental limits, or like there is upper bounds on the maximal achievable robustness that we can ever hope to achieve. And I guess Hamza will talk more about this, but I'll just mention a few points on this upper bounds that on the upper bounds of the robustness of classifiers to perturbations. So one way of basically tackling this problem of deriving upper bounds on the robustness of classifiers to perturbations is to relate it to things that we understand better. Okay, so for example, we can relate the robustness of classifiers to adversarial perturbations to robustness to random noise. Okay, so in addition to this, like we can relate this robustness of classifiers to adversarial perturbations to random noise. This also gives us insights into what is the robustness of a classifier. What does the what's basically the leverage that an adversary has when he has the model versus when he doesn't have anything about the model, right? So recall that the robustness of classifiers to adversarial perturbations was defined as follows. So it was basically the distance from the data point to the decision boundary. Now we can define the robustness of classifiers to random noise in a similar way, but where the direction now is random. Okay, so we're not taking a direction in an optimal way, but rather we're taking random rays basically, and then we're seeing how much should I go in order to go to the other side of the decision boundary. Okay, so this becomes now a random quantity. Okay, because the directions are chosen randomly, and so you can basically relate this robustness of classifiers to adversarial perturbation to robustness to random noise through this relation here. So you basically have that the robustness of classifiers to adversarial perturbation scales as 1 over root dimension times the robustness of classifiers to random noise. Okay, and you should think of the dimension as a very high number. Like for example, for ImageNet you have 150,000. So what we get here is that the robustness of classifiers to adversarial perturbation is significantly smaller than that of random noise. And there is this very large gap between these two quantities. But more importantly, if actually if your data points are bounded, then you basically get this like decay in root D of your robustness of classifiers to adversarial perturbations, which basically tells you that in high dimensions, achieving robustness is an extremely difficult task, right? And this is something that we really see in practice. In that if you it's just an empirical observation, but if you try basically low-dimensional images, you're more likely to achieve robustness than if you go to high dimensions. Basically, like ImageNet, for example, is harder to achieve robustness on with respect to smaller dimensional images. So we have this fundamental limit on the robustness of at least here it's linear classifiers to perturbations. You can extend this to nonlinear classifiers by basically saying that the curvature again of the decision boundary is relatively small, and so this result extends to such settings. So I'd like to just mention the idea of the proof without going in the detail, but I think it's useful to have a perspective on what is the relation between these two quantities, robustness to adversarial perturbation and robustness to random noise. So let's say you have a linear classifier here, okay, and again this distance here is the robustness to adversarial perturbations, and so what we're asking is how big of a sphere I can open basically around X in such a way that if I sample data points from this sphere, basically, I will get I'll get most of the points that I sample on the right side of the decision boundary. Okay, on the correct side of the decision boundary. Okay, so it turns out that concentration of measure basically tells you that if you sample data points from uniformly at random from the sphere, most of the points that you're going to sample are basically around the equator here in this shaded area, which basically tells you that most of the samples that you're going to sample are on the correct side of the decision boundary. Okay, and the bowl that you can, or the sphere that you can open until which this happens is basically scales as root dimension times the norm of the adversarial perturbations, right? So hence this root dimension factor between robustness of adversarial perturbations and robustness to random noise. Okay? Yeah. Okay, so I will just mention that these are just some ideas on the relation between robustness of classifiers to adversarial, like between adversarial perturbations and geometry, which we summarized in a review article a year ago. And there are more examples about these relations between robustness and geometry. And with that, I'll conclude. So I guess the 3 points that we had is that fooling classifiers is an extremely easy task, defending is an extremely hard task, and you might think that you are able to defend, but it's actually a very complex task. And that basically adversarial training is reducing the curvature of the loss function, which leads to an increased robustness, and that there is this fundamental limits on the robustness of classifiers to perturbations. But I guess Hamza will talk about more about this aspect here. Thank you very much.
Thank you very much. We have plenty of time for questions.
I really enjoyed your talk, thank you. So when you add on this perturbation, have you looked to see, for some examples, if you look at the image, that you can't perceive what it is, or the human can't perceive what it is? Because I guess the examples that you showed, you could still tell what the image actually was, but I'm just wondering how many of the perturbations that you've looked at you wouldn't be able to tell by eye.
So adversarial perturbations you cannot tell via the eye. Like if you compute adversarial perturbations for each single image separately, you cannot perceive basically the difference at all. However, if you're talking more about, for example, geometric transformations, yes, you will see a slight, like rotation or something like that. So you will see a difference between these two, but still you'll be able to recognize very easily the label of the perturbed image. Yes.
I'm Surajit Ray. I'm a statistician by profession, so I'm trying to understand. I mean, very nice talk, and the geometric interpretation is very nice. So when the curvature is decreasing,
yes,
what is it getting similar to a GLM? That is, you are just additively adding all the directions.
Yeah. So I should mention that it's locally linear. Because like it's just like in the neighborhood of the adversarial perturbation, it is indeed having a linear loss function, but obviously it's not linear like in the scale of, like, for example, the difference between two images. So because like if you make it completely linear, then you're not expressive enough to basically get the accuracies that we get with the deep neural networks that we have. Mm-hmm. So it's very local, the effects that I'm describing here.
And also the penalty or the regularization, yes, that you have done.
Yes.
So how is it different from, again, let's say GLM lasso?
So here we're taking the second order. So we're regularizing the second order of the loss function, right? So again, I'm not sure exactly like. So it's something that is very local. And yeah, I don't see like maybe you can explicit a bit like what kind of like relations you're expecting. Yeah,
yeah, I'm trying to say that I'm coming from a statistics angle, and I'm looking everything from that.
Yeah,
and the techniques that we use for regularization.
Yeah,
suppose we assume that it's a complicated GLM with everything linearly additive,
yes,
but obviously you cannot use thousands of coefficients, and you regularize that by saying that I will make the norm of this coefficient less than something,
yeah,
or the L2 norm of that coefficient less than something. So it's all in the coefficient space, because I'm trying to find out. There also regularization helps you bring in the parsimony that you don't overfit.
Mm-hmm.
So
yeah, so I guess probably the relation is that these two are regularizers, but they're probably doing completely different things. But I'd like to mention that actually the objective of this is not to overfit. So it's like you see, for example, that the performance on the test set after applying this regularization is actually worse than before applying regularization. Right. So our objective here is really to achieve robustness to adversarial perturbations, rather than really like maximizing our test set performance. There is this intriguing trade-off between robustness and accuracy, where you're like whenever you try to improve your robustness, you make your test accuracy basically smaller. So this is a bit different, probably from other regularizers that try to avoid overfitting, basically.
In the earlier part of your talk, when you were talking about the iterative loop,
yes,
doing adversarial training, I think you said that it had to be done sort of iteratively rather than in parallel,
mm-hmm,
and that presumably means each adversarial distortion has to depend on what has gone before.
Yes.
Can you say a bit more about how it should depend on what has gone before?
So so what I meant is basically that you need to have this. Maybe let me bring back the slide. Okay. So so what I meant is basically that if if you want to achieve robustness to adversarial perturbations, you need to compute R, the perturbation, based on the model that you have currently, right? So you cannot use like another model that like was already pre-trained or something like that, and compute perturbations on this model, and then use this as a perturbation for another model completely. You need this perturbation to be specifically tuned for the current model at the current time step t where you are basically training.
Update the weights in your system.
Yes.
You have to take account of those updates.
Yes.
In computing the new adversarial.
Yeah, exactly. Yeah. So so you need to compute adversarial perturbations for WT at time t basically. Yeah.
Given that the updates are pretty small usually.
Yes.
And you.
Yeah, so probably okay, so I was really talking about the extreme case where you're basically completely using a completely other model, but it might be robust to some extent to using like adversarial perturbations in the last epoch or something like that, but not like I was talking about like using like adversarial perturbations for time t0 for updating at time like after 100 epochs or something like that. Yeah.
Last question at the back, Sergio.
So I'm curious, so you regularize the curvature of the Hessian at the training samples.
Yes.
Do you observe that you also have less curvature in the model at the test samples?
Yes.
Does that depend on the architecture of the network?
No, so we tried different architectures and it's always the case. So it's like, yeah, it is indeed generalizing this phenomenon to test points basically. That the curvature has decreased even on test points. Yeah. We tried the ResNet architectures. We tried the, I believe, VGG architectures, and it's something that generalizes across these different networks. Yeah.
Do you think that would depend on the power of the network? If you make it more over-parameterized, I would imagine that you regularize less at the test points.
Potentially, yeah. So you're basically saying that if you make it more expressive, then you'll need to regularize less, or
the contrary. Yeah.
Okay, so if you make it more expressive, you'll need to regularize more. Probably, yeah. That's a good question. I don't know the answer to. Yeah.
Okay, we're out of time. Thank you very much, Alhussein, for
Thank you.
studying yourself today. We'll resume at 20 past. So thank you.